Hello, welcome to an edition of Visualizations with JUCE. Today we're gonna build this. It's a level meter, a staple of modern plugin UI design, the cornerstone of all things flashy in your VST. The market today is oversaturated with tons of plugins with flashy and sometimes pointless level meters. But we're going to learn to build one today nonetheless. The main point of the level meter is to give the user some sort of visual feedback as to what's happening within the plugin. You can use what you learned today in a variety of use cases. Instead of just putting it for the input and output levels, you can use it to measure detection in certain effects and frequency bands. You can use it to see what the sidechain levels are when compared to the main bus. This is not, however, a video on how to build a loudness meter. Now that's far more complicated to measure loudness, and they're usually present in fully featured mastering plugins where you actually need them. No sir, today we are going to talk about simple RMS level meters. We're going to build 3 meters today. I'm not going to show you how to do the final one, the circular one. But if you're interested, you can check out the source code of this plugin on GitHub in the description below. The horizontal meter is the simplest one, and it's really easy to do. The other two are not so hard either. They're sort of linear gradient sort of meters. The difference between them is that one is continuous and the other is discrete. This one might look discrete as well, but it's a cheeky visual trick to actually paint an image of a grill on top of whatever is being rendered. All of these are dynamically resizable as well, except for this one here, since we're actually drawing an image, and we can't actually resize a raster image without it losing resolution, which is one of the disadvantages of this method. So what are we learning today? We'll be learning about components and its responsibilities. Who is responsible for generating the level value, and who is responsible for actually rendering the graphics. We'll talk about RMS level, what it is, and how to calculate it. And finally, we'll talk about the graphics class in JUCE, and how to render these animations efficiently. Before we start off, if you want to see more content on audio programming, or generally about digital audio, do consider subscribing. It'll help the channel grow. Before we start writing any code, let's just think about the problem holistically. What are the components in our code? What's their responsibilities? And how are they interconnected with each other? So we've got the plugin processor and the plugin editor. The processor is responsible for processing the audio. This runs on the audio thread and is time critical. It has a process method, which is called back by the underlying device driver whenever the audio buffer is full. And it is the responsibility of the plugin processor to process this buffer within a certain amount of time. There is only ever one instance of the plugin processor class, and it pretty much outlives all other objects. The plugin editor is responsible for rendering graphics onto the screen. This runs on the message thread, and it's more relaxed here. There are no strict time constraints. The plugin editor can be destroyed and recreated anytime, and more than one instance can exist, but generally you have one instance of the plugin editor per running application. Now the plugin processor is only concerned with itself. It is oblivious to whatever happens around it. The plugin editor, on the other hand, is dependent on the plugin processor. It has an instance of the plugin processor, and the editor can call and access methods within the processor, but not the other way around. Right. So if you want to render a graphical meter within the audio application, then you need to do it within the plugin editor. But to keep responsibilities small and compact, we can pull out the graphical meters into a new class. Let's call it level meter. The plugin editor is composed of the level meter. Great. Now the level meters need a level to work with. Where is this level value going to come from? It has to come from wherever the audio is available. So it has to come from the plugin processor. The plugin processor essentially has all it needs to calculate the audio level values. And this is a simple calculation called the RMS value, or the root mean square value. We'll talk about RMS in a little while, But the plugin processor calculates, updates, and stores this value on a regular basis. The plugin editor will routinely fetch this value from the processor at a visual rate, say around 24 times a second, which is like 24 FPS, and feeds that value into the level meter class. The editor essentially acts like a controller or an orchestrator in this case. It gets the value from the source and passes it off to the destination. And that's the flow we're going to implement. Quite simple, right? Alright, let's get into the audio level calculations done first. So the plugin processor goes through audio samples at the sample rate. So for example, if the sample rate is 48 kHz, then you'd have 48,000 audio samples per second. That's an overload of information. We don't need anything even close to that level of granularity when we want to visually represent levels. So what we can do instead is get an average of values over a certain duration. And then that'll be our audio level. For this, we can use RMS calculations. What's RMS? It's root mean square. The definition is in the abbreviation. It's the root of the mean, or the average, of the squares of the values. Alright? But all we really needed was the average. You can get that by adding a few values and dividing it by the number of values added. Why are we doing this dance of root mean square to get the average? The main reason is that audio sample values can be negative or positive. So consider a simple sine wave which swings from -1 to +1. Conventionally calculated, what's the average? Well, it's 0 because the positive and negative values cancel each other out. So it's kind of pointless to calculate the average then if it's 0 for these kinds of polar signals. What if we calculate the RMS value instead? We get something like 0.707 for a sine wave of one period. Why is that? That's because squaring the value will actually get rid of its sign. It'll convert the value into a positive number. And since we have squared the values, we take a root of the average to balance the equation. The resultant value seems like a fairly accurate representation of the work done by the sine wave over time. And work over time in physics is the unit of power. And it's precisely what the RMS calculation is meant to represent, the electrical power in signals. Of course, electrical power in audio signals is not equal to loudness. There's a strong correlation though. When the power is high, loudness is generally high as well. But it's not a perfect measure of loudness, nor is this video meant to be anything about loudness measurements. But RMS value is close enough that it's widely adopted and used in most audio plugins and applications to represent audio levels. RMS calculations are quite inexpensive as well. When you see level meters in DAW softwares like this, they're essentially representing the RMS level of the underlying signal. There's only one variability when calculating the RMS value, and that is the number of samples to take an average of. You can either think about it as the number of samples for averaging, or as a time period or a window of time for averaging the signal within that period. So for example, if your sampling rate is 48 kHz and you calculate the RMS value of the signal for every 480 samples, you get 100 RMS values of the audio signal in 1 second. And each window of measurement is 10 milliseconds. So if you reduce the window of time to, let's say, 1 millisecond, you get more number of points, and hence more granular measurements for RMS over time. The lower the time window, the more responsive the level values are, but they can also get jittery and inaccurate during transients and bursts of volume when the time period is too small. And on the other hand, if you increase the time windows for calculation, we get a more sluggish and lazy response to the audio signal, but you end up getting a more smoother range of values. Ideally, you want to select a good sweet spot where the visuals are smooth yet accurate, instead of giving the control for the user to choose the time window. So what do we choose? How many samples do we select for calculating the RMS? In this video, we are going to keep things as simple as possible. Beggars can't be choosers. So we are going to calculate the RMS for however many samples that the audio callback provides for us. This will keep things simple yet interesting. If you want to choose a different number of samples, then you'll need to maintain a data structure, something like a lock-free queue, where you can dump values in and read it at a later time when it's filled up. You can refer to the GitHub project for this example plugin to see how I've done that. Most of the time, I found that relying on the number of samples that are provided by the audio callback is good enough. You get a decent resolution and smoothness, and we can apply a bit of smoothing later as well. Let's start off and create a new JUCE project. I'm going to choose a plugin project just because it's easier to test. I'm going to call this level meter. I'm going to leave the defaults as is. Let's create a new project. Save it where it suits you. We're going to change a couple of options in the settings pane. I'm going to give the company name as Tilt Audio. I'm going to enable this option here, which is going to add an extra line into the JUCE header file using namespace JUCE. This will just avoid me having to type the JUCE scope resolution operator before using any of the JUCE classes. Right, let's kick off Visual Studio. Before anything else, I'll quickly set up the project for local debugging. I'm going to select the Level Meter VST3 project. I'm going to right click and go to Properties. And over here for debugging configuration and for the x64 platform, under debugging, I'm going to change the command attribute from target path to the path of Reaper's executable. So you can put the path to the exe file of whatever DAW software is installed on your computer. I like Reaper since it's simple and it's really quick to start up, so I use it. Click OK. I'll right click on Level Meter VST3 again and set it as my startup project. That being done, you can actually see it in bold now. Okay, I'm going to start it off. The initial build will take a minute or so, but subsequent builds after that should be fairly fast. So it should open up an instance of Reaper for me automatically after the build succeeds. Now I'd like to just create a new project just to test this metering plugin that we're building over the entire life cycle of its development. I'll just add a reference track just for the crack. I'm going to add a new VST plugin to this track. Let's find a level meter. There it is. Just make sure that the path to wherever you have saved this project is present in the VST search path of your DAW software. Rescan it if you have to. Now there we go. We haven't actually done anything yet. All we have done so far is just set up everything we need for quickly testing and validating our changes. Let's get coding, shall we? I'll head down into the source on plugin processor.h. I'm gonna create a couple of member variables here to hold the state of the RMS values. A floating point value for each channel, essentially, so RMS level left and right. And I'm going to head into this source file. I'm going to go down to where the process block method is. I'm going to remove quite a lot of the code here. It's not really needed for us. There's a nifty little method to actually calculate the RMS here in the audio buffer class. It's called getRMSValue. It accepts a channel. So you pass in the channel that you want to calculate the RMS value of, the starting offset, which is going to be 0, and the number of samples you want to calculate. And that's in the buffer.getNumSamples. That's it. You get the RMS level of each channel. So I'm going to duplicate this for the right channel as well and change the channel to 1. The getRMS level method it's actually quite simple, right? So if I go into the method, you can see that there's a sum and you're accumulating the sum with the square of the sample. So sample times sample. And then after that, in the end, you're taking a square root of the sum over the number of samples, which is just the average. So you're taking the square root of the mean. And that's all it is. If you want to write your own function, go right ahead. You don't really have to use the getRMS level method here. But it's quite handy. It's quite small and concise, and that's really all you need to do to get the RMS value out. And as I said earlier, the RMS value is going to be calculated over the number of samples that the audio callback provides for us. So that could change over time, but generally it's around 200 to 500 samples. So I usually get 440 samples or so. We just need to do one last thing here. The range of values that you get from the RMS level calculations range from 0 to 1, which is the usual floating point gain values that you get for audio signals. But this is not a great metric for representing levels, mainly because it's linear. So you need a logarithmic skew to it. So you need these values in decibels so that the representation is more fair and accurate. Again, there is a handy convenience method for this. It's in the decibels class in JUCE, and it's a static method called gain to decibels. So it'll essentially convert the gain values that you get from the RMS level calculations into decibel values. Right. Now let's think about writing the actual level meter class. I'm going to create a new file and a new class for this. So I'm going to go into the ProJuicer project, create a new group, call it component, and let's create a new header file. I'm going to call it horizontal meter for the first one. I'll save the ProJuicer project, and it should reload all the files there. Firstly, I'm going to include the JUCE header. I'm going to put this class in the GUI namespace. I don't know why people call it GUI. That's ridiculous. GUI. I'm going to create a new class, horizontal meter, and it's going to inherit from the component class. The JUCE component class could be thought of as the parent class of most graphic components that need to be rendered out to the screen. So one of the member functions that I should override is the paint method. This is where we're actually going to draw the meter out onto the screen. Since this meter has to react correspondingly to a value of some sort, I'm going to create a member variable called level. I'll set its initial value as -60. We want the graphics to show decibel value from -60 to +6 decibels full scale. That's the idea anyway. You can change this around to suit your application better, I'd say. I'm going to go from -60 to 6 decibels in this. And I'm going to expose a setter function where you can set the value of the level. In the paint method is where all the magic happens. Firstly, we'll get the bounds of this component. Now, we haven't actually set the bounds anywhere. We'll assume that the bounds of it will be set elsewhere, and it'll be the exact size of the level meter. Firstly, we want to draw the background track of the meter. This is going to be a darker shade of white. So you can say colors of white with a reduced brightness of, let's say, 0.4. I'm going to fill the entire bounds of this with this color. I'm going to fill it as a rounded rectangle. And now to actually draw the rectangle that actually moves. That's going to be our level meter essentially. So I'm going to set this color to bright white. So we know that the level values will be anywhere between -60 to 6 decibels. So we want to translate this level value to be the width of the new rectangle that we're going to draw. If the value is -60, the width of the new rectangle that we're going to draw, it should be 0 pixels. And if it's +6, the width of this new rectangle that we're going to draw should be the entire width of the component. So I'm going to use the JMap method to actually translate from one range to another. So JMap accepts the actual value that we want to translate, which is the level. The source goes from -60 to 6, and the destination range that we want to convert it to is from 0 to the width of the component. Since this is a templated function, make sure that all of the arguments have the same type. So all of them have to be floating point numbers. We'll cast it wherever necessary. Now all we need to do is fill up this rectangle with its width determined by the value of scaled x. So it's a very simple thing to do, right? So we take the entire bounds and we remove a part of it starting from the left. So when you call bounds.remove from left, what you end up getting is another rectangle with its width as scaled x. We're going to set the same corner size as before as 5 pixels. Now we'll head into the plugin editor where we actually have to make use of the horizontal meter that we just created. So I'm going to include the header as component/horizontal header.hedge. We'll create a couple of instances of this horizontal meter class. Call it horizontal meter L and R for left and right. The plugin editor is essentially the parent, and these two meters that we have created are going to be child components within it. Let's go into the source file. To display these meters, to display any component in JUCE, you have to do two things. One, you have to add and make visible this child component. It's going to attach this child component to a parent component, and then it'll set its visibility to true. The second thing you need to do is to set its bounds. So we'll go into the resize method. We'll actually set the bounds of these two meter components. The set bounds method accepts the arguments to a rectangle. So the first two will be the x and y coordinates of the top left point of the rectangle. The third argument will be the width and then the height. So I want to say 100 pixels left and 100 pixels down. And then let's say the meter is 200 pixels in width and about 15 pixels in height. The second one is going to have pretty much the same dimensions, except move the meter down about 20 pixels from the top one. Now in the paint method, we don't really need anything here. We can fill it with an opaque background color. Let's choose dark gray here. The final thing to do is to actually refresh the meter several times a second. So for any animations to happen, we need to repaint these meters over and over again. For that, we'll make use of the timer class. We'll inherit from JUCE's timer class. And once we do that, we need to implement the pure virtual function called timer callback. This timer callback method will be called at the desired rate. So what do we need to do in this method, right? So we need to repaint the meters, of course. So we'll just say horizontal meter left dot repaint, and the right one as well. Now, just repainting it isn't enough. We need to set the value right before we paint it. So we need to get a hold of the RMS values that we just created and instantiated within the plugin processor class. Let's actually go back to the plugin processor and implement a getter method of some sort to get the RMS values. I'm going to call this getter get RMS value, and it's going to accept a channel count. So it's essentially going to give me the RMS value of the channel that I request. In the implementation of this, I'm going to assert that the channel is either 0 or 1 because we accept only stereo. If the channel count is 0, we'll return the RMS level left. If the channel count is 1, then we return the right value. Otherwise, we'll just return 0. Let's go back to the timer class, and now we'll make use of the audio processor. We'll fetch the RMS value from the getter that we just created. So audio processor to get RMS value of 0 for the left channel and of 1 for the right channel. Now that we have filled up the timer callback method, we need to actually start the timer so that the timer callback method will be called back at a certain interval. We need to start the timer within the constructor. We can either use start timer or start timer -z. Start timer accepts time in milliseconds, and hertz accepts the inverse of that. It'll be 1 over the time. That's slightly more convenient because if I want to say render the animation at 24 frames per second, I can just use start timer -z of 24. Instead, if I were to rely on the other method, I'd have to write start timer of 1000 milliseconds divided by 24. Alright, I think we have most things here. Let's give it a shot. Beautiful. As easy as that. Before we move on to the other meters, I'd like to just point out that it's a bit jittery at the moment. Take a look. It's not very smooth. The movement is sort of erratic, and there's a lot of urgency in it. So we want to just calm the meters down a little. So we want to introduce some sort of smoothing such that it's not as erratic or jittery as it is currently. There are plenty of different ways of smoothing this out. As I mentioned, if you just increase the window size, you would get a smooth value. But we can implement something better for the current window size. So here's the strategy for smoothing. If you've got a value and the next value is larger than it, then you essentially don't do any smoothing. That's because if you try to smooth values from one state to another when the value is actually going up, you get a very lazy and sluggish response for transients. So let's say there's a thwack of a snare drum or a kick drum. You want that responsiveness. You want the visual meters to actually give you the response immediately. When the value is going up, we don't do any smoothing. But when the value is going down, that's when we actually apply smoothing. If we do that, we get a responsive meter during transients. And when the RMS value is subsiding, the level visualizations decay over time. So let's implement this in code now. We can make use of a class called linear smooth value. This class is like a Swiss Army knife. This can be used in several different situations for all sorts of reasons. As the name suggests, it linearly smooths values. If you haven't used this class before, we'll explore it here. All we did here is change the RMS levels left and right to linear smooth values instead of just plain old floating point values. Once we do that, we have to call the reset method on it whenever the sample rate changes. So the best place to call this is within the prepare to play method. The prepare to play method is where all the initialization code happens. So let's go ahead and reset the values here. It accepts the sample rate and an amount in seconds for the decay time. It'll essentially mean if you set one value and if you say go to another value, it will go to that value in the amount of seconds that you determine here. Now we'll set the initial values for both of these levels. We can make use of the set current and target value method to set the value as -100. Down below in the process block, let's focus on just one of the values, the left value. Let's pull out the decibel RMS value first. Then we'll actually do the comparison. Like I said before, if the new value that you're getting is actually less than the current RMS value of the left channel, then set the target value as the new value. When you're setting the target value, you're actually saying do the smoothing essentially. Your current value is some value, and then you're providing a certain target value. Over time, within the decay duration, the current value will tend towards the target value. If the value is greater than the current RMS level, then we set current and target value. This means it'll just directly jump. There won't be any smoothing that happens here. Now these values don't smoothen on their own. You have to explicitly call a method to progress time and to move the values. Usually, if you're doing it sample by sample, you call the getNextValue method on it. Since we're accessing by block and not by samples, we're going to call the skip method and pass the arguments as the number of samples. This means that every time the value is smoothed over the number of samples that you provide. Now down below in the getter method, we were previously returning the floating point value. To get the floating point value out of the linear smooth value instance, we just call the getCurrentValue method. And that's pretty much it. We should have achieved some sort of smoothing now. Let's find out. I'll build the application again and we'll see what the smoothing looks like. As you can see, when the transients hit, the level meters jump forward. But whenever there is silence or when the sound settles down, the values are smoother. In this way, we get an advantage of a smoother range of values while retaining the responsiveness and chirpiness of the meters. Alright, so on to the second meter then. So this one is a vertical meter. It's sort of got a linear gradient going on here. So at the bottom there's green, and at the top there's red, and the middle is yellow. This is a strategy behind drawing this particular meter is we're gonna draw something continuous that goes from green to red. And on top of that, we'll paint a grill of some sort, just an image of a grill, and then we'll overlay that on top of the meter that we draw. That'll give us the perception that it has holes in it and it's sort of illuminating through the holes. So we'll start off by creating a new file as usual. We'll call it vertical gradient meter and we'll save it. We'll set up this file as we did previously. We'll include the JUCE header, put it inside the GUI namespace, and create a new class here called vertical gradient meter. It'll extend the component class from JUCE. Over here, we'll override the paint method. I want to try and adopt a different strategy of getting the values in this class. Previously, we had a private member called level. We exposed the setter method to set the level value. This time, we're going to try and build something self-sufficient. We're going to have a child meter class, which is completely self-sufficient and self-reliant. It should know how to fetch its own values, and it should also be responsible for repainting itself. Previously, we had exposed a setter method to set a value for the levels. This time, we'll instead have a function pointer. A pointer to a function, when executed, will actually give us the level values. So we'll call it value supplier. And we need the function pointer to be supplied at some point of time. We can put that in the constructor. So the constructor of the vertical gradient meter will accept a value function. This can be an R value reference. The double ampersand expresses that it's an R value reference. It's usually used during move semantics. So essentially we want the value function to be moved into the value supplier. It's just a simple way of instantiating something by moving rather than copying. We'll get a better idea of what the value supplier is and how we actually pass the value of the function method soon enough. Till then, we'll assume that whenever we call value supplier, we will be getting the latest value of the level. After that, let's get the local bounds of the component. Now we'll set the background color of the component. The meter's background color will be black this time. After that, we need to draw the meter itself. We need to create a color gradient now. So we'll use the color gradient class in JUCE. It accepts a few arguments. The first one is the starting color. Let's say it starts from green and it starts at the very bottom. And then the color flows to red. And that could be at the top of the component. And we're trying to do a linear gradient and not a radial one. So the last argument will be false. Now this doesn't actually get you yellow in the middle. You have to explicitly add a new color. The way you do this is by add color method on this instance. We want to add a new color halfway between green and red, and this new color is yellow. Instantiating a new color gradient class is, well, it's a bit expensive. It creates and stores a lot of colors underneath. Since the color gradient doesn't change, it can be moved out of the paint method. We can try and put it in the constructor, but then the bounds aren't available in the constructor. The bounds of the component are not set during construction of the component. It's set later when you're actually calling set bounds of the component. So the best place to instantiate the color gradient would be within the resize method, which will be called every time the component dimensions change. Let's have a private member variable called gradient, and let's instantiate this here. Now within the paint method, we set gradient fill on the graphics object that we get with the new gradient that we created. Now we need to map the level values from its original range of -60 to 6 to the new range of 0 to the total height of the component. We'll call this scaled Y. Next, all we do is fill the rectangle with the bounds and then remove the scaled Y amount of it. We take a chunk out of the bottom of the bounds with the height as scaled Y. This will give us the actual meter component that needs to be drawn. Now, since this class manages its own values, it could be argued that it should manage its own repainting whenever required. So this class could inherit from the timer class, and then call start timer HC of 24. We need to override the pure virtual function timer callback, and in this method, we simply just call the repaint method on the component. Previously, the parent component, which was the plugin editor, used to do this. This meter is truly self-sufficient. Now all we need to do in the parent, create a new instance of it and make it visible. As before, let's include the new class component. Let's create a couple of new instance variables of the linear gradient meter. Since the linear gradient meter has a constructor which accepts the function pointer essentially, we need to initialize these instances within the constructor initializer list. And this is where we pass the function pointer. We'll create an anonymous function here using a lambda essentially. If you're not too familiar with lambdas, they're essentially functions that you don't really have a name for. But the syntax can be a little confusing, so I'd really suggest getting a primer of it somewhere else. We're expecting a function with a signature which doesn't accept anything but returns a floating point value. And within the body of this function, we'll just return audioprocessor.getRMS value of the 0th channel. And since audioprocessor is outside the scope of the lambda itself, we need to pass it by reference. We'll do the same with the right channel meter as well. This time, we'll get the RMS value of the first channel, which is the right channel. We add and make visible these components. I'm going to slightly increase the height of the parent component just to accommodate these new level meters that we're drawing. And in the resized method, we'll set the bounds of the vertical meters. They can be 100 pixels from the left, let's say about 200 pixels from the top, and a width of 15 and a height of 200. The right channel meter will have something similar, just offset the X value by about 20 pixels. Let's see what it looks like. That's pretty cool. We have a solid, continuous linear gradient meter, essentially. Now for the cheeky visual decorations on top. I've got an image of a grill here. It's just like a metallic grill of sort, which has holes in the middle. And this is a PNG image, and it's transparent as well. It's really quite simple to create one of these. If you have Adobe Illustrator or Inkscape or any of those vector design softwares, you can just create like a big rectangle, make it a little rounded, and create tiny rectangles and just duplicate them. And select everything and just say subtract whatever is in the front. And then voila, you get a meter or whatever looks like it. You probably put a drop shadow on it and you're done with an asset. Let's pull this asset into our project. I'm going to create a new folder within our project. I'll call it assets, and I'll put the PNG image inside it. I'll drag this folder into the ProJuicer project as well, and then save it. If you've never dealt with images or binary data in ProJuicer, you will have access to the binary data within your project. So let's get back to the class. I'll create a new instance of an image class, and I'll call it grill. Now I'll fetch the actual binary data which represents my PNG file. I can get this from image cache, get from memory. The binary data is embedded within the binary data class as static members. The first argument that it accepts is the actual binary data itself. The second one is the size of this data in bytes. Now I could draw this image at the end of the paint method after drawing everything else. But since I'm drawing this on top of everything else, it sort of makes sense to leverage the paint over children method. Let's draw the image. Let's call the draw image method within the graphics object. This accepts a drawable or an image, which is going to be our grill instance. And we're going to fill the entire bounds of the component. Now let's get back to the resized method of the parent. Now we've said it's 15 pixels wide here, but we kind of need to change it because since we're dealing with raster images, we want to try and retain the same size of the raster image. So if I inspect the properties of the image, it says that it's about 200 pixels in height and 25 pixels wide. So let's use those dimensions. One last change that I'd like to make is that I can go back into the paint method of the component, and over here I'll reduce the size of the actual drawable area of the meter itself. The grill occupies the entire component size. You want the meter itself to be slightly smaller in area so it fits nicely into the grill and not overflow. I think if you've done everything right so far, it should be good to go. Let's see what it looks like. That is neat. That's pretty much what we were aiming for anyway. Let's talk about one more meter today. It's this one, the discrete meter. It's got little bulbs that turn on and off based on the level values. You can configure the number of bulbs that you want in your plugin. It's essentially to make a discrete meter widget without the need for drawing a raster image on top. It can get a little more complicated, but again, the principle is quite simple. So if you observe this meter widget, you can see that each bulb is black when it's turned off, and then when it's turned on, it's got a little black outline, and then it's filled by a solid color. The color depends on where the position of the bulb is in the meter. And it's got this slight glow, an outer glow effect. So that's what we need to implement. As usual, let's create a new file. And I'm going to call this vertical discrete meter. Let's save the project. I'm going to copy the contents of the previous meter that we just made, the linear gradient meter. We're going to use this as the base, and we're going to start from there. I'll rename the class the vertical discrete meter. I'm going to get rid of things that I don't need in this, namely the image, and I'm also going to get rid of the paint over children method. I'll clear out most of the paint method as well, because we'll start from scratch there. We'll hold on to the linear gradient object that we created earlier. And we'll continue to use the value supplier method of getting the value and making this entire class self-sufficient as the other one that we just did. Now for the bulbs themselves, let's make a class to represent each bulb object. I'll call this class bulb. It'll extend component. The state of the bulb can either be on or off. I'll maintain a member variable for the state. I'll call it isOn. I'll set it to false initially. And I'm going to expose a setter method here to set the state of the bulb. The color of each bulb doesn't change over time. So what we can do is create a member variable for storing the color, and we can get the color value during construction. I'm going to override the paint method within the bulb class. Within the paint method, we're going to get the bounds first. The bounds of each bulb is set within the meter class itself. So we'll assume that some amount of area is allocated for each bulb. Since we also want to represent a glow, let's reduce the size of the bounds of the actual bulb itself. And we'll reduce it by an amount of 4 pixels each side. We might need to reference this 4 pixels later, so we'll pull it out and we'll call it delta. So to draw the basic shape of the bulb, we will draw a circle within this bounds. Now if the width and the height of the bounds are exactly the same, meaning if bounds is a square, then it's all well and good. We can just inscribe an ellipse within that bounds and we would end up getting a perfect circle. But let's say the bounds isn't a perfect square. Let's say it's a rectangle where the width and the height are not the same. If we were to draw an ellipse within that bound, we wouldn't get a perfect circle. To avoid that problem, we'll just get the smallest side and make sure the bounds that we are drawing the circle in is a square. Jmin will give us a minimum of 2 values. So we'll query jmin of width and height. And this will be the side of our bounds. Now let's create the actual bounds that will fill up the bulb. And this will be a rectangle of the same x and y as before, with the width and height as side and side. If the bulb is on, we'll set the color to be the actual color that was provided to us during construction. If not, we'll color it black. To actually draw the ellipse, we'll use fill ellipse from the graphics class. After that, I'll put an outline stroke on the bulb. I'll set the color to be black. I'll use the draw ellipse method to draw the outline stroke. And I'll set the stroke width to be 1 pixel. Now if the bulb is on, we also want to draw the glow as well. The glow that's emitted by the bulb. The way we're going to achieve the glow effect is to have a radial gradient whose opacity decreases over distance. We'll use the color gradient class again. The starting color will be the same color of the bulb, but with a reduced alpha. Alpha here is just opacity. I'll set the alpha to be 0.3. This color is going to start from the center of the bulb bounce. And towards the edge of the bounce, the color will fade away with its alpha being 0. But also, I'll increase the lightness of the color so that it has more whites. The second point here is sort of pointless. You don't really need it if you're setting radial gradient to be true. The last argument is radial gradient, so I'm going to set that to true. Now you can pull this radial gradient out into the constructor or into the resize method like we did previously, because nothing really has to change here. But I'm going to leave it up to you guys to do it. Now to apply the glow effect, we'll fill the ellipse with this new gradient color. We'll use the bulb fill bounce. If you remember earlier, we constrained the size of the bulb bounce by an amount of delta. Now the glow effect needs to protrude outside the bounds of the bulb itself. So for that, we'll expand the bulb bounce to include the extra 4 pixels on each side. And that's the bulb class done. Now to actually use the bulb class within the vertical discrete meter class. We can hold on to a collection of bulbs here in the main class. A good data structure to go with is a standard vector. So a std vector of bulb would be the way to go, but we can't actually do this. If we try to do this, we'll end up getting plenty of compilation errors. The reason is that a JUCE component is not copyable and it's not movable. And you can't have non-copyable items within a vector, because when the vector resizes or when the vector components are added, it needs to be either copied or moved. And JUCE components allow neither. And one of the workarounds for that, and you'll come across this quite often when you're dealing with a collection of components, you'll have to use a vector of unique pointers of the component. So we'll use a standard vector and a standard unique pointer of bulb. And we'll call the collection bulbs. We'll also define a total number of bulbs that we want to use. I'm just going to use a constant integer here of 10. But of course, this can be configurable during construction or dynamically resized as well, if you want it to be. Let's assign some space for these bulbs. So in the resize method, I'm going to get the local bounds first. So I'm going to chop off parts of the bulb bounds and assign it to each one of the bulbs. So let's figure out the bulb height first. The height of each bulb is essentially going to be the total height of the component divided by the total number of bulbs. So that'll give you the height of each bulb. Now in the resize method, I'm going to clear all the bulbs from the collection and re-add them over here. Now we need to iterate through the collection of bulbs. We could use a for each loop here, but the positional index is kind of needed in one of the places. So we'll use the standard old-timey way of writing a for loop. For I equal to 0, I is less than the total number of bulbs, and I plus plus. We'll create a new bulb instance here. And since it needs to be a unique pointer, we'll say std make unique of a bulb. And the constructor of the bulb accepts a color, if you remember. How do we get the right color? Starting from the bottom, the color of the bulbs will be green, going up to yellow, and then to red. Since these are discrete bulbs and there are only about 10 of them, we want to get a distinct color from the gradient. So I'm going to say get color at position from the gradient. A position is a value, and the position has to be a value between 0 and 1. So I'm going to say I divided by total number of bulbs. That will give us a value between 0 and 1. When the color is at the bottom, it will give us a value of 0. The color is at the top, it will give us a value of 9 over 10. Never really get red, but you know, that's how it is. Once we've created a unique pointer of the bulb, let's add and make visible this component. And then I'll set the bulb bounds. And while I'm setting the bounds of the bulb here, so I'm going to take the bulb bounds rectangle that we created, and I'm going to chop off, starting from the bottom, the height of the bulb. As this loop iterates, more and more chunks are chopped off from the bottom of this bulb bounds rectangle. And finally, we push this newly created bulb into the collection. And just for efficiency's sake, we will move it instead of copying the unique pointer. Now the last thing that we need to do in this class is to essentially activate and deactivate the bulb as necessary based on the level value. The level value is available to us in the paint method. Now let's make a decision for each one of the bulbs. So let's iterate through the collection of bulbs that we have. So if the level value is greater than I plus 1 or index plus 1 divided by the total number of bulbs, we'll set the state of the bulb at that index to be true. Otherwise, it'll be false. The idea here is, let's say for example the level is 0.25. This would mean the first two bulbs at the bottom would be activated, but not the third one. These 4 lines can essentially be written in one line, like this. But it's sort of cumbersome and hard to read, so I'll leave the judgment up to you regarding which style you would rather use. One more thing I forgot, and coming back to this after a while, is the level. We assume that it'll be from 0 to 1, but actually the value supplier will give the level in decibels. We need to map the decibel values back into the original range of gain. So we want to say map the level value given by the supplier from its original range of -60 to 6 decibels to the new range of 0 to 1. That's perfect. Now let's go back to the plugin editor and we can include the new file here. Include component /vertical discrete meter.h. I'll create new instance variables as before of the vertical discrete meter. And in the constructor, we know the drill. We'll initialize them in the initializer list. And we'll provide the value supplier function. And the constructor will add and make visible these components. And in the resize method of the plugin editor, we'll assign some space to these new meters. So we'll set the left discrete meter's bounds as 200 pixels x and 200 pixels y, 25 pixels in width and 200 pixels in height. And we'll use pretty much the same dimensions for the right meter. We'll translate horizontally by 30 pixels. I think we should have everything. So let's try build it. Well, there you go. If you've got any questions or problems, hit me up over here and I'll try to answer them. All the code is on GitHub, and the link is in the description below so you can check it out there. Also, let me know your thoughts about the format of this video. It's quite tightly edited, and I've sped up the video as well so that you don't have to sit and watch me type. Well, I've got more ideas on what to include in the next visualizations and JUCE series, but if you've got any suggestions, hit me up here. Until next time then.